Hi everyone, welcome back. So in this video, we will discuss about device model and Sysfs in Linux kernel. So let's get started. So this is the content that I will be discussing in this video. So first we will go through the different type of devices. Then we will go through the device model. So basically device model each consists of these three structures. We will understand each of them. And at the end, we will discuss about sysfs and kernel event layer. So mostly in Linux, we assume that we have major three type of devices. First one is block device. So these are the examples like hard disk, CD-ROM, floppy disk. These are called as block device. And the second one is character device where we read the data byte by byte. So and these are like mouse, keyboard, joystick. And third one is network devices. So it consists of routers, modem, repeater, and other components. So let's deep dive little into different type of devices. So as I have already mentioned that character devices are the devices which we access them byte by byte in sequence of characters. So and in kernel we access the device with the help of this character device node. So if you visit /dev and uh, there you will find the character device. So this is a this path we call it as a character device node. So here we can read or write on the device uh, based on this path, and this is the structure by which we represent a character device. uh, so similarly to the character device we have a block device node where we can read or write, but the block devices are different from character device that uh, in block devices we have the block of bytes. So like we have block of bytes, so that's why we say it is a block. So here we can access the device in the form of block. And also like these block devices are generally associated with some kind of file system because we implement file system on the block devices. Uh, Also, the address of a block device we can randomly access. Like in the character device, sequentially we have to read the data. Here we can read the data in whole device, any address, at the any address. A network device are little different from other two devices. So here we access the network device based on the socket API. So the socket is represented with the help of this struct socket. And we have other devices also. Those are not actual device, so that we call them as the pseudo device. So these pseudo devices are created by kernel only for some functionality. So let's take the example of this dev underscore random and dev slash unrandom. So if you see, if kernel want to generate some random number, then it will access is at this device and it will get the value of a random number. So this is just for the internal use of the kernel. Similarly, we have other devices. Those are virtual or pseudo. They are not the actual devices. So in our kernel, most of the devices are hardware devices, but we can have the illusion of a device by the pseudo devices. So like if you want to differentiate between the actual device and a pseudo device, then you can do that based on the uh, major number and minor number. So I will discuss about it more in coming slides. So I am not going to deep dive more into the different structures. I am presenting this slide to just show you that we have a specific structures to represent a device or like different device like block device and character device and the network device. So these are the structures that exist inside a kernel. So in kernel we can represent every device and associated structures are there. So let's say if you want to see the all the device in the /dev directory. So remember that all the devices are listed here in /dev, and then whatever comes, this is the device name. So if you want to list all the devices present in this directory, then you can do this, go inside dev and then do ls minus l. So it will show you the all the devices. So if you go through this, this is a listing of the device. So the first character of this listing tells which type of device it is. So here you can see it is a C, it is D, it is L, it is D, and these are the like these are the other fields. So like this is a user or this is a group. So these two fields are important. These fields are major number and minor number. So this is a major number, this is minor number. So this is minor, this is major. And if you see here, so this C represents character device, D is directory, so this is related to file system, and L is a link. So L is for link. It is not a actual file or a device, it is linking to some other device. Similarly we have this B, so this B represents this, that it is a block device. So in this way you can identify which what are the different kind of devices in our system. And this major number and minor number we will discuss in some other video. So major number basically tells uh, a class of a device, and like if we have a uh, 5 floppy disk, then each floppy disk will have the same major number, but to differentiate between the different floppy disks, we have different minor numbers. So let's now understand the relation between the kernel and the devices. So if you see this structure, you can see that devices are separate from the operating system or kernel. So to connect kernel and the devices, we have device drivers. So the responsibility of device drivers is that we have to communicate whatever device is going to say to the kernel or operating system. And similarly, if kernel want to access the device, then also it is facilitated by the device driver. So device driver is kind of a module that runs into the kernel and and provide the functionality to the device based on the requirement of the kernel. So it is kind of a module, as we have already discussed in our previous video. So let's now see the different devices connected in our system. So the connection of devices, we call it as a topology. So if you see, or like as we all know that in a computer or a mobile, we have CPU, we have this GPU also, we have modem, we have this DDR RAM. So these are the buses, those connect them with each other. So in this way, we can see that we have different components interconnected with each other. So if like we are not seeing hardware from outside. So if you want to see what are the different kind of devices in my system, that we can do with the help of this device model. So that's why in kernel we have a device model. So with the help of this device model, we can picture every component in our system. So as we go further inside the slides, we will know how we can picture that. So this slide is important, so that's why let me go in this slide line by line. So if you see, it is saying that it generates a complete and valid tree of the entire device structure of the system. So this device model will create a whole complete tree of all the devices connected inside a system, including buses and interconnections. And second is saying that minimization of code duplication. So like if we have a character device, then we will represent that character device once. So if we are representing that device again in somewhere else, then we will just create a link. So it is we try to minimize the code duplication in that way. And also like from this we can say that reference counting is global functionality. So like if we have some device, if multiple services of kernel or processes is using the same device, so from the reference counting we can increment and decrement based on the usage of that particular device. And this question will be very obvious after we discuss in the coming slide, so I will address this question later. And also, like, it also categorize the devices based on the classes. So classes means like it is a output device or it is a input device. So we have a specific class, we can view the devices in a based on the functionality, so in that way we call them as a classes. So like if we don't know the internal physical device topology, how they are connected, but we want to know the devices that do input and output in, so those kind of things we can do with the help of this device model. And this I have highlighted it in the yellow color because this is the main reason for creation of the device model. So it was for the power management. So like we have different components, so there should be some sequence how to power up the device and how to shut down the device. Then only our system will work properly. So there should be some sequence how. So like if you want to power up the device, then you have to power up the leaves first, then go towards the root. And if you want to power down the device also, then at that time also we have to power down from the leaf and go up to the root, so in a correct order. So let's now discuss the core part of the device model. So that we have already seen that it is made from these three structures. So let's deep dive into all these three structures one by one. So let's now discuss about k object. So this k object structure is to represent a device inside a system. So you can say that k object is equivalent to a device. Okay, so remember this, it is important. So k object is representing a device, so we have related fields here. So these are the important fields that I am going to discuss in this video. So this is a name, so here we can give the device name like I2C bus. And this is a entry of, like, this is the structure which contains other k objects. And this is important, like inside a k object we can have another k object pointed to the parent of a parent k object. So like we have device 1 and then dev 2 and dev 3. So in this way, like if we have a one k object for this device, I mean k object for this device, then parent will point to this k object of this device. So in this way we have a hierarchy or tree like structure between the k objects. And this is a Kset and K object type. So these are the two other important structures. So these are the part of the K object structure, and we will discuss about these two structures in coming slides. So this is important for the file system, Sysfs file system. So that we will see in coming slide. So this entry tells that where this device will be listed in the Sysfs directory structure. And this is the kref. Kref means kernel object, k object reference. So this is just a counter to tell how many instances of this k object is being used inside a kernel. So if you know that this represents a device, so this should be part of a device structure. So if you see here, cdev, this represents a character device. So inside the character device structure, we have this k object structures. In this way, we are relating a device with the k object. So there is a direct relation between a device and a k object structure. So let's now see about the k types structure. So k types structure just tells like the type of the object. So I mean, like if we are having a devices kind of like input devices or output devices, so all the input devices will have the same behavior and output devices will have the same behavior. So if you want to define the devices which are having same behavior, then we can have the same k obj underscore type structure. That's why this is a part of a k object structure as we have seen here. S- So this tells that default attributes or like the attributes we can see it as the properties of a device. So if like we are having a file, we are having a block device, then we can read and write. So these attributes you can say that these are the properties to how to read and how to write. And these are the Sysfs operations. So like these attributes will be present in the Sysfs file system. So there we will represent these attributes as the files. So so when we will represent these as a file, at that time this sysfs operations will tell what read and write behavior or other operations will be on these files. So we in this function ops structure we can define different kind of functions that and the behavior that we can do on these attribute files in the sysfs file system. And this release function is this release function is called when kref of a k object becomes 0. So this will be called when kref is equal to 0. So when kref becomes 0, at that time this release function will be called and it will deallocate the k object structure related for particular device. So here you can see that it is saying that K, Ktypes describes default behavior for a family of K objects. Or in other terms, you can say that family of similar devices. So this is a Kset. So Kset structure tells that the all the similar devices should be in the same group. So as its name suggests that it is a set. So it is a set of similar behavior devices or uh, identical behavior devices or k objects in terms of k objects. So if you see here, it tells that it uh, like it is a base k object, and this is a list of all the k objects inside this k set structure. So this is a list of similar k objects, and this is a log if you want to do something. So this is a here we have this u event operation. So u event means user events. So if like this tells the hot hot plug behavior of a device. So like if you are uh, inserting or removing of a device, at that time what should be the behavior of the device in the k object structure that we define with the help of this sorry u event ops. And these things we have already discussed that the main purpose of this case set structure is to group together the similar devices, and those similar devices will be having the same k types because those similar devices will be having the same behavior. So behavior is defined by k object type structure. This thing I have already mentioned in the previous slides, so it is just a redundant thing. So let's now picturize all these three structures. So it is quite of confusing because these structures are interrelated and part of each other. So let's picturize it in the terms of kernel. So if you see, kernel is built from different subsystems. So within that subsystem, we can have similar behavior devices. So those similar behavior devices are represented with a Kset, and this Kset is a list of all the k objects those are similar to each other in the behavior. So that's why these are showing to each other, these are related to each other. So this top level k object uh, becomes a directory like represent the upper level device, and others are like dependent devices having the same behavior. So like uh, if you want to represent this in the sysfs file system, at that time it will be a directory. So as in the previous slide we have saw that in the sysfs k object individual directories in the file system. So here you can see that like here you can say this is a directory on directory 1. So within this we will have multiple directories 1, 2 and 3 and 4. So this is a top level directory. Inside this we have multiple directories. So all these key objects will be related to one directory in the sysfs when we create a sysfs based on this behavior of kset and k objects. So this represents kind of a uh, uh, this directory structure. Let's now further see the pictorial view. So if you see here, this is again the same representation of previous slide. So if you see, these arrows tells good thing. So like if you see here, this black says that these are the part of this same k set. So they are reflecting back here. And if you see this, this is saying this is a parent. So this base k object is kind of a parent to other k objects, and that's why in the previous slide I have shown you that this is a parent child and relationship between the directories in the sysfs file system. So it actually represents the relationship between all these three uh, structures. So let's now see how we can create k object and we can use them. So this is a function k object in it. With the help of this function, we can initialize a k object, and we have to provide the k object structure and we have to provide the k object type, because every k object is representing some behavior of a particular device. That behavior of a device we can represent with the help of k object type. So this is a one way, or we can initialize in this way. So like if you see, we we allocate the memory for the k object, then we set the k set field of that structure. So if you see here, this my k set and my k type, we are allocating them based on our requirement. So we have to categorize the devices based on our understanding how we are using trying to use that particular device, and that device is represented with a k object structure. If you don't want to do these things, it is already implemented with the help of this function k object create. So it will directly create a k object and it will return a pointer for this k object structure. So let's now discuss the reference count. So as we have already discussed that reference count tells the uh, count of the object that is being currently used. So you can say that count of the object currently in use. So if some kernel code is using this k object or device, at that time it will run this function k object underscore get. So in this function what we will do, we will increment the reference count, and when the use of that k object is done, then that particular code or kernel code will call this function k object put. So in this function what we will do, we will decrement the reference count. So before using the reference count, so here if you see, reference count is just a atomic variable which we can modify. So when we first time reference a k object, at that time we initialize the uh, reference count. So here if you see, this is a atomic variable, so we are doing some atomic operations and we are setting this variable to 1. And when we are running the gate, at that time we are atomically incrementing the reference count, and when we are putting the k object, at that time we run kref underscore put function. So if you check here, we are just decrementing the kref. So release internally will decrement the not release, sorry, here we have decrement and test. So it will decrement the reference count and it will check. So these are the different functions internally. When we call this kobject get, it will uh, call this function, and when we will say kobject underscore put, it will call this kref put function. So let's now look into the sysfs file system. So just look into this picture. I have put this picture in the first slide of sysfs because you have to make the pictorial view of this thing, so it will help to understand the further slides on sysfs. So if you see, this is a slash sys. So we mount the sysfs uh, in this directory, and there we have different directories like bus, devices, classes. So if you see, buses can be I2C, SPI, and devices can be platform. So if you see, like, it is just a pictorial view of the whole system, how different uh, devices are connected to each other. So this is the purpose of sysfs, to just visualize the interconnections of the devices inside a system. So that we have already discussed, that we are, it is a virtual file system and it is mounted at slash sys, and it provides the device topology of a system in the form of a file system. So we have discussed this attribute in the kobject structure. So these attributes relate to a specific file, and in the file system, and we can do some operations on them to to tell something to the particular device. So we have a code snippet. I will tell you how we use them. So this statement is very important. So how we are building this sysfs file system based on the k objects. So if you see, if you go back here and revisit the k object structure, so if you see, we have this node, kern fs node. So this is the directory entry that tells where this device will be showing in the sysfs, and directory entry is related to a file. So in that way we can represent this as a file system, virtual file system. So this directory entry is concept of a file system. So this is the field that relates the kernel object and the file system. So with the help of this field, we are having a particular field in a file system, and this parent field provide the different hierarchical structure. So like we are going from level 1 to level 2, and this way we are building the whole structure based on the k objects, because we have parent. So based on the, as the as the structure of the k objects is there, we have this entry of directory entry in the file system. So based on this hierarchy, we also build the file system in the sysfs file system. So this statement is stating the same thing, so that I wanted to clearly mention. So if you go in the slash sys and do ls, you will find these, whatever picture we have seen here. This is the just a pictorial view. If you actually go into the kernel code and see, then it is representing the same thing. So like we have different subdirectories, and within subdirectories we have different related fields, files and directories. So like there can be devices that goes into different directories, but those directories will represent only via the symlink, if it is not direct hardware of that particular directory inside. So that's like, in that way we are saying we are not uh, misusing the duplication. So let's now see how we can add a k object in the file system. So this is a function we can run, k object underscore add. So it will add an entry inside a sysfs, and similarly we have this function k object delete. So it will delete the k object entry inside the sysfs file system. So like in the in the K object structure, we have this field attributes. Okay. In the, yeah. So here in the K obj underscore type, we have this attributes field. So this is a attribute. So this is a structure of attributes. So it contains a name. It is a kind of a variable or a file inside the file system. It has the owner and it has the mode permissions. So like if we have read, write or execute permission, and to operate on these attributes, we have this sysfs of uh, operations. So if you see this statement, it is saying that this function will be invoked uh, when we read that particular file or attribute. And this is the store function. So this is a function that we will invoke when we are writing to that particular attribute or a file in the file system. So I am using attribute and the file interchangeably. So attributes in the file system is as a file. So we export the attribute of the K object. So attribute is a concept of K object, and when it goes to the sysfs file system, then we call it as a file. So this is the same thing. So if you see here, we have different arguments. So if you see, like here we are going to read the data from this buffer, and we will read the data of this attribute into the buffer, and similarly here we will write this data of the buffer to the attribute. So this is a way we can create the file from the attribute in the sysfs file system. So this is a function sysfs underscore create underscore file. Like I have already mentioned that sometimes that device or the functionality is not the actual device, and we are linking to some other device. So functionalities will also be linked. So that we can do with the help of this sysfs underscore create underscore link. So it will create the link with that target, and the name of that name of that attribute will be the name as it is. This is the variable, whatever name we give in this variable. And these are the functions that will remove the attribute from the file system, and this function will remove the link from the file system. So file system is very organized view of different devices and different devices based on the different functionalities. So if we go back and visit again, so if you see, the block directory represents all the block devices. Buses directory represent all buses related devices. And class is a higher like overview based on the just overview, like different kind of devices. And dev had different kind of like block devices, character device. So we have different conventions to organize sysfs uh, in a nicer way. So we say that whenever we create a system sysfs attributes, it should be per value per file. I mean one value per file. So we have to just read single value. Like if I am writing an integer, then only single integer we can read and single integer we can write. And it should be text based. And type of that variable can be C types. Whatever C is supporting, that type we can map to that particular attribute or a file in the sysfs. And this is kind of a kernel to user communication. So sysfs provides the kernel to user interface. So if kernel want to communicate something to the user, it will write that value to the sysfs attribute, and user can read that value from here. And similarly, if a user want to communicate something to the kernel, then user can write to some attribute of his device, and then that will read by the kernel, and it will instruct the device to do something. So this is a device. So if you can say that sysfs is kind of an interface that helps to communicate uh, between to make the communication between user and kernel. So let's now see uh, the demonstration of different functions that we have seen. So if you see here, this is a k object create and add. So in this way, we create the object and add into the sysfs file system. If you see here, we are creating a attribute. So first we have to define attribute. So here we are defining the attribute in this manner. We are providing the permissions. We are providing the operations that we can do like sysfs show, sysfs store, and here we are implementing the sysfs show and sysfs store. So basically here we are just reading the value of this variable to the buffer, and here we are storing the value of this buffer to the this attribute. So in this way, this attribute will be created here. And if you want to access this attribute ext attribute, at that time when we access this sysfs show function will be called. When we write something, this sysfs store function will be called. So if you see here, if I am doing echo 123 and this sysfs attribute or file, because it is represented as a file. So when this statement will run, at that time this sysfs store function will be called, and the value of this ext value will be changed. So and when we read that value of that attribute with the help of this cat or some other command, at that time this sysfs show function will be called, and whatever we are doing, it will do that thing. So if you want to know more about all these structures and implementation in a driver, this is a good source for you. So you can go to this link and so see the different how it is implemented in a proper way. This is just a single snippet of this link. So let's now discuss the kernel events layer. So basically half of the content of this slide we have already discussed. So this is kind of kernel to user notification system based on the based on top of the Kobjects concept. So this is just to like there are some important activities that kernel want to communicate to the user. Like if our disk is totally full, that our kernel can notify to the user that your disk is totally full, or like temperature of the processor is very high, at that time also we can notify to the user, and something like that. So we have, and like we have different events that we can tell to the user. And in this statement it is saying that each event has a optional payload, and kernel event layer presents payload as a sysfs attribute. So if kernel want to notify and tell some data, that like if we are saying that processor is very overheat, at that time we can also tell that what is the temperature of the processor currently, so that we will update in a some file or attribute in the sysfs file system, and that value user can read and know that what is the current temperature of the processor. So in this way kernel will try to communicate to the user space. So that's all for this video. And in conclusion, we can say that we have discussed about the different type of devices, and then we have discussed about different structures like k object, k set, and k types that help to represents the devices and devices interconnections of a system in the kernel. And based on the k objects, we can build sysfs for clean view of the whole system, and we can see different category of the devices in different directories of a sysfs. So that's all for this video. I will see you in the next video.